All right, so I'm very excited to introduce our last invited speaker for today, Aryan and Makhtari. He actually recently started at UT Austin as an assistant professor. Before that, he graduated from UPenn and spent some years at Simon Institute and also at MIT. And he has done amazing work and inspiring work in the line of convex optimization and also non-convex optimization, as well as their applications in machine learning. Earlier this afternoon, you have already heard some talk that mentioned about optimistic gradient descent ascent, and he's going to give us some very interesting insights and also theoretical fundamental understanding of this algorithm. So without further ado, let's welcome Aryan. Yeah.
Thank you very much, Neo, for your kind introduction. Hi, everyone. Welcome to this talk. Today, I'm going to talk about understanding the role of optimism in minimax optimization, in particular, a proximal point approach. This is a joint work with Sharat Patatil and Asu Zaglar, both from MIT. So in this talk, we're going to focus on minimax optimization problem, which is also known as saddle point problem. So I'm sure you all know the formulation. You have a minimax formulation where x is your minimization variable and y is your maximization variable. And we don't assume any constraints in this problem. So this problem has been around, the minimax optimization problem has been around for more than decades due to its application in game theory, control theory, and robust optimization. But recently, it has received a lot of attention, in particular because of its application in training generative adversarial networks, also known as GANS. So to see the connection between minimax optimization and GANS, let's take a look at the setup that we have in training GANS. So you can think of this problem as a game between the generator and the discriminator. Basically, the goal of generator is to get a noisy signal and generate some fake data in a way that it's hard for the discriminator to distinguish fake data from real data. And the goal of discriminator is to come up with a classifier that can distinguish fake data from real data. So they have this game going on, and at each time where a generator chooses a noisy signal and generates fake data, and the discriminator distinguishes whether it's a fake data or real data, then we can see the output of this process, and depending on the fact that the discriminator did the correct job or the wrong job, and the solution is true or false, they're going to receive some signal from the output of this process so that they can update the model that they're using for basically the generative and the discriminative phases of this problem. So as I mentioned, this can be considered as a game between the discriminator and the generator. And for the same reason, it can be formulated as a minimax optimization problem. But what makes this problem more challenging than the standard methods, the standard formulation that we have seen so far, is that both the generator and the discriminator are neural networks. And the problem that we have is non-convex, non-concave. However, still in practice, many times the algorithms that we use for solving these non-convex, non-concave problems are the standard tools that we have used for solving convex-concave problems. One of the most popular algorithms for solving this problem is called gradient descent ascent. I'm going to refer to that as GDA. As the name suggests, the update is pretty simple. When you want to update your minimization variable, you just compute the current gradient, and you follow the update of gradient descent. And for updating the maximization variable, you follow the update of gradient descent, but gradient ascent. So it's a gradient descent ascent update. But one of the other algorithms that has received a lot of attention for training GANs is actually optimistic gradient descent ascent. It is also known as OGDA. What's different between OGDA and GDA is this term that we have here in red, which is called the negative momentum term, or also known as optimistic term. So what's interesting is that if you're coming from an optimization background, typically when you want to add momentum, the coefficient of the momentum is a positive coefficient. But here, if you look at the minimization update, you can see that the coefficient for the momentum term is negative. And instead of having a momentum in terms of variables, we have a momentum in terms of gradients. So this is kind of strange, but somehow this extra negative momentum term, or the optimism term, it helps to train GANs significantly better than just vanilla GDA algorithm. To better highlight this point, let's just take a look at the following example that I'm borrowing from the paper by Daskalakis and his collaborators. So basically on the left, you see the images that are generated by following the update of Adam. And the images on the right shows the images that are generated by following the update of optimistic Adam. So when I say you follow the update of Adam, you follow Adam for descent for the update of X, and Adam ascent for the update of Y. And optimistic Adam has this additive negative momentum term. And as you can see, the images that are generated by the update of optimistic Adam, they are more diverse and they have higher quality. So even in practice, this algorithm does work better than GDA. And then a natural question to ask is why this optimistic term or negative momentum term helps us to do a better job in solving these minimax optimization problems. And of course, there have been several results looking at this notion of optimism for min-max problems. And if you look at the history of optimistic methods, it was first introduced in 1980s by Popov as a variation of extra gradient method. Later in 2013 and after that, it was also rediscovered in the context of online learning and used as optimistic mirror descent method, online optimistic mirror descent method. And also recently in 2019, there is also another paper that you can think of OGDA as a variant of the forward-backward algorithm that has been proposed in this paper by Malitsky and Tam. But these works mostly on the introduction of this algorithm, but there have been several works that have tried to study basically the convergence property of OGDA algorithms. They look at its limit point properties, the convergence rate of this algorithm in convex concave, strongly convex to strongly concave, or bilinear problems, or also stochastic versions of min-max optimization. But in this talk, we're going to take a different path. We're going to look at optimism or negative momentum as a way to approximate proximal point method. Basically, the take-home message is this. OGDA can be interpreted as an approximation of the proximal point method. And to show this connection between the proximal point method and the optimistic gradient descent ascent, we're just going to first focus at a very simple problem. This problem was actually mentioned in the previous talks, and we already have seen that if you follow the update of gradient descent for the simple bilinear problem, you're going to have a cyclic behavior. So now let's dig into this. So you have a bilinear problem of X transpose Y. It has just one solution, one saddle point, which is the origin 0, 0. If you follow the update of gradient descent ascent, or GDA, the update can be simply written as the form that we have here, because the gradient with respect to X is just simply Y, so the gradient at the current point is just YK, and if you compute the gradient with respect to Y at the current point, it's just simply XK. So if you follow this system of updates, which corresponds to GDA, you're going to see that the distance to the optimal solution is going to grow over time. So not only you cycle around the origin, the distance to the optimal solution is actually growing. And this is a very simple algebra that you can do. But if you do the update of OGDA for this simple bilinear problem, you're going to see that actually the iterates approach the optimal solution, the origin. And to see the connection between OGDA and proximal point method, let me also mention the update of proximal point method for solving the simple bilinear problem. The difference between proximal point method and GDA is that instead of computing the gradient at the current point, you compute the gradient at the next point. So it's an implicit algorithm, or you can think of this as a backward Euler discretization instead of a forward Euler discretization. So the update of X is computing the gradient with respect to X at the next point, xk plus 1, yk plus 1. And the same thing for the update of Y. And as I mentioned, the only difference between this update and the update of GDA is that it's an implicit algorithm that you compute the gradient with respect to next point. And of course, in general, it's not easy to implement this algorithm because it's an implicit algorithm, and it requires computing inversion of an operator, which is not easy to do in general. But for this specific simple problem, as you can see, you can rewrite this system of equations as the simple update that you can easily implement. And if you look at the convergence property of this algorithm, proximal point method, you can show that actually the distance to the optimal solution is becoming smaller at a linear rate, where the rate is 1 over 1 plus eta squared, where eta is your step size. So it's pretty nice. So you follow proximal point method and OGDA, they both converge to the optimal solution. But that's not the punchline of this example. The important observation is this. If you look at the convergence paths of OGDA and proximal point method for this problem, they're almost identical. Or we can say that OGDA does a very good job in approximating proximal point method. So by looking at this example, you might think, OK, maybe OGDA can be interpreted as an approximation of proximal point method, which is exactly what motivated this work. And in this work, basically, we're going to look at OGDA as an approximation of proximal point method for finding a saddle point. And we show that the iterates of OGDA are order small eta squared approximation of proximal point iterates, where eta is the step size. At the beginning of the talk, I'm just going to focus on the convex concave problem, and I'm going to show that basically by using this proximal point approximation viewpoint, you can show that the iterates of OGDA are going to stay in a bounded set without assuming any constraint or any compactness for the constraint set that you have. And as a result, you can show that the function value converges to 0 at the rate of 1 over k. Function value converges to the optimal objective function value at the rate of 1 over k. And we're going to also use this perspective of studying OGDA as an approximation of proximal point method to also extend the analysis of this algorithm to other cases, such as bilinear problems, strongly convex, strongly concave problems, and so on. And at the end, we're going to revisit another famous algorithm, extra gradient, using the same perspective. And we're going to show that extra gradient can also be interpreted as an approximation of proximal point method. And using this viewpoint, we can come up with a very simple analysis for extra gradient method for these considered settings. OK, so this was just a toy problem that I discussed, but let's focus on the general setting that we have in mind. So we have a saddle point problem. The function f is convex with respect to x, and it's concave with respect to y. F is continuously differentiable, and the gradients are Lipschitz. And I'm going to refer to L as the constant of Lipschitz continuity of the gradients. And the goal is to find the saddle point of this problem, x star, y star. And we know a saddle point of this problem has this nice property that at a given point, x star, y star is the best choice, and at the point y star, x star is the best choice. So to make this connection between the proximal point method and OGDA, let me just formally mention the update of proximal point method. If you have seen a proximal point method for a minimization problem, you know it's just a function plus a proximal term that is form of x minus xk squared, right? But here, since we have a minimax optimization problem, you need a proximal term for the minimization and a proximal term for the maximization. And this is going to be the update that you're going to have. And if you write just the first order optimality condition for this update, you can simply see it's what exactly I mentioned in the few slides back, where the update for x and y is computed by computing the gradient at the next point. So it's an implicit algorithm. And as I said, the only difference between this algorithm and GDA is the point that you're computing the gradient. So this is this may not be the algorithm of choice for solving min-max optimization problem, because as I said, it's not always computationally cheap. But what's nice about this algorithm, the analysis of this algorithm, proximal point method for convex concave problem, is very easy. And you can easily show that you're going to converge to the optimal solution at a rate of 1 over k. Now we hope, since OGDA, we think it's an approximation of this algorithm, we hope to use this perspective to come up with the same convergence theory for OGDA. But before talking about OGDA, let's think of a way of approximating proximal point method. If I cannot compute the gradient at the next iterate, a natural thing to do is say that if the variation of my gradients is small, or it's not changing, then hopefully the difference between the next gradient and the current gradient is more or less close to the difference between the current gradient and the previous gradient. Using this simple logic, you would say, OK, the next gradient can be approximated by the current gradient plus the difference between the current gradient and the previous one. Right? So it's just assuming that the variation of gradients is small. If you have this condition, then this is a natural thing to do. And if you replace the gradient that you need for the proximal point method with this approximation, what you get is exactly the update of OGDA. So OGDA can be also interpreted as an approximation of proximal point method with the fact that you assume that the variation of gradients is small. So now let's take a look at a better way of understanding the difference between the iterates of these two algorithms. So the previous slide shows the connection between OGDA and proximal point method, but let's make it formal. So if you start from point xk, yk, let's call x hat k plus 1 and y hat k plus 1 as the point that you obtain by performing the update of proximal point method on xk, yk. And let's call xk plus 1 and yk plus 1 as the point that you update by performing the update of OGDA on xk, yk. Now I want to see what's the difference between these two sets of points. And we can show that actually the difference between these two sets of points is order small o of eta squared. The interesting part is if you do the same analysis for GDA, instead of a small o, it's going to be large O squared, eta squared. So that means that OGDA does a better job in approximating proximal point method. And because of this property, it does converge for some cases that GDA does not converge. And using the logic that I just mentioned, we could show that OGDA converges to the optimal solution at a rate of 1 over k. Everything is the same as GDA except the constant that is multiplied by the error to the optimal solution, which is just a factor 4 larger than the rate that you would get for proximal point method. So it's pretty tight, and it's very nice, and it gives you the first convergence guarantee for OGDA in convex concave problems. And since this is a very simple interpretation, the proof is actually super simple. So think of this. I can rewrite the update of proximal point method with error as this, where you have the update of proximal point method plus some error in the x update and in the y update. And hopefully, this error is in a way that you can implement the algorithm in a very simple and computationally efficient way. And by having this error term, you don't lose anything in terms of convergence rate. But what is important is that the main tool for analyzing proximal point method is this 3-point equality formula, which is also, which I think was proposed by Nemirovsky, which shows that if you think of z here as the concatenation of x and y, and fz as the operator that is the concatenation of the gradient with respect to x and the negative of the gradient with respect to y, you can show that proximal point method satisfies this equality without the last term. But if you have an additive error term like the one that we have, you're going to have an extra fourth term there, right? And what you can do, you can just say, OK, for OGDA, this error term is nothing except this fzk plus 1 minus 2 fzk plus fzk minus 1. If I replace epsilon k by this is the inequality that I'm going to get. And just using Lipschitz continuity of the operator, you can show that the inner product from 0 to this inner product, when you look at the sum of this inner product, it's bounded above by this upper bound that we have. And since the operator is monotone, the left-hand side is just non-negative. So I can simply conclude that Zn minus Z star squared is always bounded by a constant factor of Z0 minus Z star squared. So, and this C is actually order 4. It's either 4 or 8. So you can show that you never go beyond the bounded set around the optimal solution. So using this boundedness, I can say the right-hand side of the first inequality is just a constant times this. And since this term is an upper bound for the distance to the optimal solution, using convexity and concavity of f, I can show that the error of average iterate is just bounded by a constant over n. So after n iteration, your error goes down at the rate of 1 over n. Very simple proof, actually, using this proximal point approximation idea. So far, I just talked about OGDA and thinking of this algorithm as an approximation of proximal point method. But you can also come up with the EG algorithm if you come up with a different approximation for proximal point method. So remember, this was the update of proximal point method. I can do a simple, a kind of weird update and replace xk plus 1, yk plus 1 here in the gradient, y the update that I have for xk plus 1. And basically rewrite the update as this. So you can easily see that xk plus 1 here can be written as xk minus eta gradient with respect to x of f of xk plus 1, yk plus 1. So these two systems of updates are equivalent, right? The only thing that I'm going to do, since the inside one is less important, I'm just going to replace xk plus 1 and yk plus 1 with xk and yk. So what's the new update that you're getting? So you're updating xk by computing the gradient at a point that is sort of like a midpoint for you. And if you just simplify this update, you're going to see that you're basically doing the update of extra gradient method. So you first find a half point or a midpoint by following the update of gradient descent for x and gradient ascent for y, and then you use the direction of the gradient that you get at this point to update your original model, which is the update of EG. And using this, the same perspective, I can show that the iterates generated by proximal point method and EG also the order small o eta squared away from each other, which is exactly the same approximation that we had for OGDA. And as I mentioned earlier, this is better than the approximation that you would get if you follow the update of GDA. And since you have this approximation, you can of course show that the rate of convergence is 1 over k, as we showed for as we showed for OGDA. But it's also interesting to see that for that bilinear problem that I discussed at the beginning of the talk, also EG does a very good job in following the update of proximal point method. So this intuition sort of makes sense that EG is also an approximation of proximal point method. And we can get a rate of 1 over k without assuming a compact constraint set for the problem, which is the rate that has been shown by Nemirovsky in 2004 for convex-concave problem. Although it was later extended to the unbounded set by Monteiro and Sveiter, but this was under a different termination criteria, which is different from the termination criteria that we have here. And we think this is the first result that gets a rate of 1/k with this function value termination without assuming compactness for the optimization problem that you're solving. Okay, so far I just talked about convex-concave problems, but of course you can use the same perspective to analyze OGDA and EG for other problems that have more structure. For example, the bilinear problem or the strongly convex-concave problem. And for these algorithms, you should be also able to show a linear convergence rate, because as we know, it's possible to achieve a linear rate in these two settings. But before reporting the result, let me just mention that in the bilinear case, we define the notion of condition number as the ratio between the lambda max of B transpose B, where B here is the matrix that you have in the objective function, over lambda mean of B transpose B. And this ratio sort of behaves like the condition number of the problem. And for a strongly convex, a strongly concave problem, we definitely know the ratio between the Lipschitz continuity of gradient and a strong convexity is the condition number. But here you have a min-max problem. So mu is the minimum between the strong convexity of X and a strong concavity of Y. So for the bilinear problem, again, using the same perspective of analyzing OGDA as an approximation of proximal point method, you can show that you have a linear convergence rate where the constant of linear convergence rate depends on the condition number. It's 1 minus 1 over kappa, basically order-wise. And the same result holds for EG using this approximation technique. And of course, for a strongly convex concave case, you can derive the same result for both OGDA and EG. And if you write the complexity bounds for these algorithms, we basically have shown that OGDA and EG have an overall complexity of order kappa times log 1 over epsilon, where here kappa is the condition number of the problem. As I said, this is the results for the bilinear and strongly convex and strongly concave cases are not new. I mean, some of these results have been proven by Paul Sang, Liang and Stokes, and Giedel and his collaborators. But basically, the whole point of this part, the part that we are talking about bilinear and strongly convex and strongly concave case, is that you can come up with a unified way of analyzing these algorithms without assuming any specific structure for the problem. So you just think of these algorithms as an approximation of proximal point method, no matter what setting you have, and then you just derive the approximation technique to analyze these algorithms. And what's interesting, and I want to highlight here, is that we basically have seen that for all these three cases, convex-concave, strongly convex, strongly concave, and bilinear, OGDA and EG outperform GDA. For instance, in the bilinear and convex-concave case, GDA may not converge. It might diverge, actually. And for the strongly convex case, GDA, the best known rate for GDA is kappa squared log 1 over epsilon. So in all these three settings, OGDA and EG outperforms GDA. So we also use this perspective of thinking of OGDA as an approximation of proximal point method to come up with a generalized version of OGDA. So there was this consensus that when you want to run OGDA, the coefficient that you have for the step size, or the step size parameter, should be equal to the parameter that you choose for the negative momentum term. But we basically show that using this proximal point approximation, you don't need to choose this alpha and beta equal to each other. And for a wide range of choices of alpha and beta, we could show that the same convergence guarantees still hold, and you don't need to necessarily choose these two parameters equal to each other. And I would like to highlight that this general formulation covers the update of GDA, and if you set beta to be 0, and update of OGDA if you just simply say beta is alpha. So to summarize, basically, we studied the notion of optimism through the lens of proximal point method, and we showed that it is possible to analyze OGDA as an inexact approximation of proximal point method. And using this, we came up with the first convergence theory for OGDA for convex-concave problems, and we also recovered the known results for bilinear and strongly convex, strongly concave problems. We also used this perspective to revisit extra gradient algorithm and show that it also can be considered as an approximation of proximal point method, and this viewpoint gives us a simple way to analyze extra gradient method for all these three considered settings. And also, at the end, this interpretation also aided us to come up with a generalized version of OGDA that we do not need to set the step size to be equal to the momentum parameter that we have for the negative momentum term in the update of OGDA. And as a future direction, I think the most fundamental problem that we face here is that we use this formulation and this work to just come up with an idea, to understand the rationale behind the update of OGDA. But what is more challenging is to extend this the analysis of this algorithm to more challenging settings, such as non-convex concave problem, where one side of the problem is easy, the maximization is convex and easy, but the minimization is not easy and you have a non-convex function. Or the general weakly convex, weakly concave case, where it's in general non-convex, non-concave, but it has some structure. And it would be very interesting to show that for these general settings, you can still reach the same conclusion and show that OGDA outperforms GDA for all these considered, for all these mentioned setup. Okay, so let me stop here. Thank you so much for your attention, and I will be more than happy to answer any questions that you might have. Thank you.
Any questions? You can come to the mic if you have any questions. Yes?
Hey, thanks for the talk. So you provided an analysis for the strongly convex concave and for the strongly convex, for the convex concave one. What about an analysis for the stochastic one? Because since you are doing a perturbation analysis, stochastic method are sometimes analyzed as like perturbation of the gradient method. So
that's an excellent point. Basically, so you're saying that we can think of a stochastic method as an approximation of the original deterministic method. Indeed, so maybe it's possible. We haven't explored that avenue yet, but it would be reasonable to also follow first to come up with an analysis for the stochastic variant of proximal point method, and then see using that and this result that we have to come up with an analysis for the theory of a stochastic OGDA or EG. That's a very good point, actually.
Yes?
Yeah, so I'm a bit confused with the 1/k rate for the convex concave when you look at the function value.
Right.
So I'm trying to kind of just interpret that because, for example, in the bilinear setting, let's say I set x equals to 0 or y equals to 0 when you have x transpose y, then the function value is 0, but
right.
You know, it has nothing to do with the equilibrium. So I'm trying to just understand the semantic of your suboptimality there.
That's a very good point. Actually, this is a notion that has been developed and used by Dembrovsky in his book, in his paper, where you are looking at this lower bound actually can be upper bound. This can be upper bounded by mean of f of x and y star minus f of x star and y. And if you look at this duality gap, this is basically an upper bound for what we have. Since we can show this duality gap is going to 0 at the rate of 1/k, you can reach the same conclusion for the average iterates. Basically, that's, yeah.
So just to be clear, you're saying your rate is on the duality gap, not just on this difference of function values like you show in the slide.
No, but we are looking at the convex-concave problem, and for the convex-concave problem, this is the typical natural thing to use. But for the bilinear problem that you just mentioned, that you might have 0, 0, the error that we characterize is the distance to the optimal solution. For that one, we are not looking at the distance between the optimal objective function value and the current objective function value.
Thank you.
Thank you. Yes?
Congratulations for the talk. So if I understand the purpose of all of that, we need to understand the unified theme about all the optimistic methods.
Right.
And actually, this is very useful because in multiple conferences, we're listening to different approaches, and it is very nice to have a unified approach. So my question is the following. Do we have any intuition about the continuum analog of all of those? For example, for the GDA, we have the gradient flow plus and minus. But do we have a continuum case? Because it would be really interesting to see if finally all those methods are one continuum analog that we just discretize with different notion. And actually, maybe we can use knowledge from numerical analysis that exists already, how those different methods fail or succeed. Do we have any notion about that?
That's a very good point. So remember, the ODE that you have for proximal point method and for GDA, they're identical. They're just the outcome of two different discretization. One is forward Euler, one is backward Euler. And the OGDA tries to come up with the approximation of the better discretization, which is more robust. We know implicit discretization is more robust comparing to explicit discretization. But they all follow the same dynamics, if you think of the continuous interpretation of these algorithms, basically.
Thank you very much.
Thank you.
Yes, so a very quick question. So in your talk, you mentioned the analysis of two algorithms, extra gradient and optimistic gradient descent. But which one you recommend in practice?
So in practice, at least for this bilinear problem, as you could see, OGDA does a better job in approximating proximal point method. But for some of the experiments that we look for convex concave problems, actually EG does a better job in converging to the optimal solution for convex concave problem that we studied. But in the worst case scenario, they could be basically identical.
All right, thank you.
Thank you.
Hi, so your results for a convex concave setting were like average iterate convergence, but for like proximal point and for extra gradient, if you like decay the step size, you should be able to get some sort of last iterate convergence. Have you thought about like proving rates for last iterate?
That's a very good point. So we didn't look at the last iterate convergence for these algorithms, and we just, at least for the convex concave case, all the results are in terms of the average iterates.
Sure.
Indeed, it might be possible to use a diminishing step size to say something, or like an averaging technique over the iterates to come up with a last iterate convergence. But I'm not sure if you're not going to lose anything in terms of rate. That's something that I think needs further investigation.
Sure. Thank you.
All right. I think we can take one last question. Yeah.
In fact, this is just a comment. I'm not sure if you are aware of our work in this conference on the analysis of stochastic single co-extra gradient methods. So in this paper, we have also the 1/T convergence results, and we studied the stochastic optimistic gradient descent method.
Thank you so much for pointing. Actually, I have seen that paper, and that's also another excellent way of analyzing OGDA for convex concave. But I think the paper was posted on our archive after we posted on our archive, but I think that's an independent work. But the way that you analyze the OGDA, I think is a little bit also different from the perspective that we have. But I appreciate bringing that up. Thank you so much.
Thank you.
Okay. Actually, we're pretty ahead of time, so if you guys have any more questions, feel free to ask.
Regarding the continuous analysis and the discretization, so in continuous time in the bilinear case, we don't converge actually, right? Like if in the gradient flow. And I guess this is the property of the discretization that makes it converge,
That's
right?
a very good point, actually. Yeah. You're absolutely right, but for the convex concave problem, you can think of these algorithms as discretization of this gradient flow, and there are different discretization, basically. I've never actually thought about this. You're right, actually, if you follow the gradient flow, of course, you're going to cycle around it, and depending on the way that you choose the discretization so that it gives you like sort of like inside momentum, you get to the solution, or if not, you might even diverge. But that's a very good point.
Yeah, thanks.
Thank you.
Any other questions? Okay, we do have some more, yeah.
Thanks for the nice talk. So I have just a quick question regarding, there are some recent work, I guess you might be know of, it's like we do the minimax convex concave, but even strongly convex concave, but on the inner loop, they have an oracle of the update.
I see.
And then that will have like, there's actually one recent NeurIPS paper I came across, they said that the close gap of the lower bound of that kind of rate is 1/k². So I'm wondering how does this kind of simultaneous moving update compare to those kind of results?
I don't think you can get 1/k² for convex concave problem. Actually, if you consider all the computation times of because I think there's an example.
Strongly convex concave.
Strongly convex, strongly concave.
Strongly convex concave.
Oh, that problem we didn't study that. I think you're right. For strongly convex concave, you can get 1/k². But they have a subroutine for one of the updates. Yes. I have seen that. But actually, we didn't study that setting. But it would be interesting to see what OGDA and EG, at least OGDA, does in this setting, and if it's possible to get a rate of 1/k².
Oh, by the way, one quick thing is that it seems that in those type of formulation, different from this one, is that they have the compactness of Y and X. So is that essential, like, is that a key difference here?
Here we never had any compactness analysis, any compactness assumption, and all the results are without assuming anything about the constraint set. So, which I think is one of the strengths of this analysis. But I'm not sure what exactly they have in their analysis, if they need heavily this compactness assumption or not.
Yeah,
but it would be interesting to explore that direction.
I see. Great. Thanks a lot.
Okay, thank you. Any other questions? We can take more questions. And meanwhile, I'd like to ask the Spotlight presenters to come to the front to get set up. I do want to ask actually two questions. One is following up Simon's question about like the convergence criterion you're
Yes.
using is mainly for the function values, not
Yes.
necessarily the duality gap, right?
Right.
Is that the main reason why you can allow for unboundedness
Actually, we
of
have
the...
that one as well. But the way that we report the result is just in terms of average. We also have this duality gap in the paper. But the way that I'm reporting it here is just in terms of the distance between x star, x average, y average, and x star, y star.
Okay, but that's for the strongly convex case,
For
right?
strongly convex and strongly concave case, we just report the result in terms of x. The distance between x and x star and y star. We don't look at the function value.
Okay, and for the general convex concave case, you are saying you also have
Yes.
result for the
Yes.
duality gap. And also another question is, you know, this extra gradient methods can be easily extended to, say, Bregman divergence cases where you can develop this mirror prox algorithm. And I was wondering how this proximal point framework can be generalized to Bregman divergences.
That's a very good point. I think I had the same question when I was reading Nemirovsky's paper, Mirror Prox, but I haven't still figured out a good connection between the Mirror Prox formulation that he has and this proximal point method. But that would be something interesting to also take a look at.
Okay, yeah, thank you.
Thank you so much.
Yeah, if we don't have any more questions, let's maybe just thank one more time for our
Thank you
speaker
so
for this exciting talk. Yeah.